So please turn on your cameras so I can ask everybody to turn to participate. Also, please don't make us waste time, okay? If you are not here, you're not here. So if I call somebody and that person leaves for any reason, yeah, you can do it. But the problem is that you make us waste time. And that's something that we don't have too much. Una posibilidad es de que para aprovechar esto, yo necesito.
La computadora tiene como una mesa. Tirada.
En la segunda hora, y estos puntos de luz se funciona. Sí, ahí va. Ok, entonces en la segunda hora yo tomo. Este cable. Yo creo que sí llega. Al menos que llegue aquí. Ese es el primero que conectó ayer. No. Quizás hasta aquí nomás llega. Sí, no más. No, hasta ahí nomás. Ok, ahí nomás me queda. Ok, ya.
Sí.
Ya. Daniela, would you please start recording?
Yes, doctor.
Okay, so you're recording. Good morning, students. Today is Thursday, 19th of May. We're going to start the material, okay? I assigned you something to review yesterday, so we're going to start by that, okay? This is not a test. This is just to be able to answer if there is any concern about this material, okay? So let me share this, hopefully. Okay, Daniela, can you see my screen?
Yes, doctor.
Okay. Screen?
Yes.
Okay, let's see the last in the list here. Mis Puertas, what is the reaction? Mis Puertas, what is the reaction, please? What is
Good morning, teacher. Doctor, sorry. A reaction is an effect when you It's like, let's say, like you react to something that is happening that moment. The effect.
I need one adjective in there. And the adjective that I need is external. Okay? The reaction, I'm sorry. Okay. Are you still, can you still see my screen?
Yes, doctor. Right now, yes.
Okay, because I made a change here. Let me close this and start it again. Okay, a reaction is an external. That's something, oh man, Jesus Christ. Reaction, it's an external force. That's very important, okay? So that means that if it is a force, that means that it needs to be calculated, external force, okay? And it has to be with the support, okay? Developed by the support. Now, what it does is it prevents from that end or that point moving in a certain way, okay? Prevents a point something. So, for example, if you have something like this, okay, this does not allow this motion or that motion. And to complete this, to prevent this, it develops forces, which are the reactions in the vertical, in the horizontal direction. Okay. Now, we continue. If we have a simply support, then we have two versions, okay? This is a simply support, and this is also a simply support. Okay, but in this case, since we have wheels, this point cannot move in the vertical direction, but it can move in the horizontal direction. This one here, this and those motions, those two motions are prevented. Okay, so let me see if I can change color. That means that in this case, we're going to develop a reaction in the Y direction and a reaction in the X direction. These are the reactions. In this case, we're going to have a reaction, the vertical direction, because that motion is prevented by the support. In the case of the clamped end, okay? In this case, okay? Mr. Medina, what happens in this case? This case here, in the clamped case. What motions are prevented?
Repeat, please, the question.
No, I don't have the time. See, the motion is this and the rotation. Okay, so those two motions are prevented. That means that in this case, we're going to have a reaction, okay? A reaction in the vertical direction and also a moment. So this moment is developed by the support in order to avoid this rotation, okay? Since we're saying that those are external actions, that means that those have to be calculated when we do the analysis, okay? And then we have the, let me go back to the previous color. Then we have a guided. A guided is kind of difficult to draw. It's something like this. And this end, okay, is allowed to move in the vertical direction, okay, but it cannot rotate. So it's something like this. So it's, let's suppose we have a little plate here, and this end is welded, okay, but it can move vertically. So we have little wheels, little wheels, little wheels. So these little wheels allow this end to move vertically, but the rotation is prevented. So in red, those are the motions which are not allowed with these supports. Since you're not allowing this support, this type of motion, that means that you need a moment, okay? In this case, we have to include a moment. So in this case, the reaction is going to be a moment, okay? So let's call it M sub R because this is a reaction, okay? So you see that in every type of support, you have a different reaction that we have to calculate. Because we said that these are external, so we need them to consider their motion in order to be able to complete the calculations. And finally, when we have a spring, okay? Okay, let's suppose we have here a spring, okay? This is like a partial situation, okay? If this thing moves in the vertical direction, let's call it V, this guy here reacts with a force, okay, presents a force. So this is the reaction in the vertical direction, okay? So you have it there. Different supports, they prevent a certain motion, and according to the direction of the motion, they develop reactions, okay? So those, they have to be calculated if you want to proceed with the analysis, because these are external forces acting on the system that we want to analyze. Okay, Ms. Valdez, what is an internal force? Ms. Valdez, what is an internal force?
Is the reaction?
No, you cannot use the word reaction. No, it's not a reaction. Mr. Carriel, what is an internal force?
It's a force that acts in the structure.
Now that's a very general, I mean, because you are also describing an external force. An external force is also, but it's different. Miss Arechua, what's an internal force?
Are force in the own beams, but the structure. In the structure, the own beams.
No. People, if we have an structure, let's call it a general structure. Okay, let's say this is the structure I want to analyze. It's a potato. Let's suppose that we have some supports here. I have a spring here and all of that. And let's suppose that we have forces. These are external forces. Okay, let's suppose I have a moment here. This is in static equilibrium. Let's suppose that it is in static equilibrium. Okay. All of these, we can talk about internal force. And we say, okay, let's suppose we want to analyze up to here. So we make a cut here. This is what we call the method of sections. Okay. Now, if we consider this part here, so I'm going to write it on here. Okay, that's the part that we are analyzing. Okay, now here, this is the cut. We have a support down here. There is an external force here. Okay, so this is this part here. Okay, but this is part of this system, which is in static equilibrium. Okay, now, if we want to consider that in static equilibrium, then we have to consider in this cut the action of this other side on the segment that we are analyzing. Okay, So it's what does this part do on the segment that we want to analyze? Those are the internal forces. So for this to be in equilibrium, you can see that if you have a force pointing to the right, will rotate. But this is in equilibrium because this is part of the whole system, which is also in equilibrium. So probably we need a force in this direction, in the vertical direction. Probably we need a moment, and we need another moment like this one. All of these are internal forces, and they appear when we make a cut and apply the method of sections to analyze a segment, a part of the structure. Mr. Pesantes, are you with me? Mr. Pesantes?
Yes.
Okay, are you with me? Did you understand what I just said?
The shared forces and the bending moment.
No, no. See, what I'm explaining is what is an internal force in general, okay? So in general, internal forces are going to be 6, 3 forces and 3 moments. All of those are internal forces. Now, the next step is, this is the general case. This is a 3D case. That's what I wrote here, okay? All of these forces and moments. And the problem is that if we consider problem, okay, that's going to be a little bit complex. Okay, so what we do is we study a little bit simpler systems. And usually those systems are in a plane. For example, let's suppose we want to analyze this type of structure, okay? We have this, we have that, and we have a force like here. Okay, on the left, I'm going to write the reference system. This is X and Y. Okay, in this case, I can make a cut here, right? Because this is in a static equilibrium, okay? This, and in this cut, okay, in this cut, we're going to have internal forces, okay? In this case, this is a frame in the plane. How many internal forces do we need to consider, Mr. Nieto? Mr. Nieto, how many internal forces do we need to consider for this case? For the case of the plane, we are working only in the plane.
In this code, 2 forces.
Only 2?
In this code, the force axial.
The axial? Okay, those is, we call it P. Please, if somebody is writing on my on the screen, don't do it. Okay, I don't have the time to waste it. If you want to play around, go to somewhere else. I'll just stop my class and that's it. I don't have the time for jokes. Okay, so I have this force. This is an internal force, okay? You see here that in here, in blue, that's the system. These are the internal forces. This is an axial force. And from now on, P, large P, is going to be used to describe the internal force in the X direction. Go on, go on. What other force do we need? Internal force do we need? What other internal force do we need?
The force normal.
Bending moment.
The bending moment, okay, that's this one here. So this is what we call M sub Z. So this is the moment in the Z direction, okay, which is perpendicular to the face. I'm missing one, another force. Histapia, the shear force, yes, yes. So this is this one here. So this is notation. This is notation that we're going to be using in this class. Okay, P is an internal force in the axial direction, in the X direction. V is similar, but in the Y direction. And M sub Z is the bending moment in the Z direction. Okay, so in case of a plane, or an structure in the plane, these are the 3 internal forces that we will be working. In the case of a beam, okay, we have only lateral load. And in that case, it will be even less. We're going to have only two internal forces, which are V and the bending moment, shear force and bending moment, okay? In the general case, you need 6. In the plane, we need 3. In the case of the beam, it's a special case of an structure in the plane. We're going to need only 2, okay? Mr. Dominguez, Salim Dominguez, what is an statically determinate system, Mr. Dominguez? What's an statically determinate system?
It's a system that is, we can use the formulas to determine
Yeah, but what formulas? What formulas?
the static equilibrium.
Exactly.
Equation.
We can use the static equilibrium equations for what? To calculate what?
The internal forces.
No. What can we? Miss
the
Valdez,
actions and moments.
Miss Valdez. What is a statically determinate system? We just said that we
When we can calculate the reactions by
Exactly.
using the static equilibrium
exactly.
equations.
We can use static equilibrium equations to calculate reactions. Okay, so I don't know if I have another. Okay, we're going to be there. Okay, so for example, in the case of the plane, like this one here, okay, in general, we have in the case of the plane, how many static equations do we have? Mr. Villalba, how many equations do we have?
3 equations.
Exactly. What are those static equilibrium equations?
For y direction, x direction, and the summatory of the moment.
Exactly. In the case of the plane, we have summation of forces in x, summation of forces in y, and summation of moment in the z directions. Okay? So we have 3 equations. So in the case of a plane, if you have more than 3 unknowns, unless you can include another geometric relations, that's not an statically determinate system. Okay? In the case of the beam, okay, usually we have only 2 equations of equilibrium, okay? Because we do not apply forces in the x direction. We only apply forces in the vertical direction. So we have summation of forces in y and summation of moments. Okay, so in that case, if we have more than 2 reactions, unless we can apply any other type of geometric relation, that's going to be an indeterminate system. Okay, in this part of the material, we work only with the determinate systems. Okay, and then in after a few minutes, we will say that we work not only with the equilibrium equations, but we also include a material relationship. And that will allow us to analyze another type of system, the indeterminate systems, okay? But so far, yes, you're right, we have only 3 equations, so that's the total number of reactions that we may calculate. Okay, let's go on. In the first case, Mr. Jordan Chiriboga, is this a determinate system, Mr. Chiriboga?
I don't know. No.
Okay.
But
Mr. Iturralde? Mr. Iturralde? Mr. Ramirez? Is this determinate? Ms. Santos, is this the determinate?
Yes, doctor.
How many reactions do we need to calculate?
3 reactions.
Exactly. In this point here, let's call it point A. Okay. What are the reactions that you need to calculate?
A in Y direction, A in X direction.
So that's the reaction in Y direction and also the reaction in the X direction, right? That's 2. And what's the other that you need?
At the point B, the other side.
Okay, let's go on the other side. Let's call point B. And that's what reactions do you need to calculate?
Reaction in Y direction.
Exactly. So that's this one, reaction B in the Y direction. So we have 3 unknowns. 1, 2, 3, and we have 3 equations of equilibrium. These are summation of forces, moments, and forces in 2 directions and moments. Okay, let's apply the first one, which is the easiest. I'm not going to do it completely. I will let you do some calculations. So we said summation of forces in the X direction. Okay, so right now I'm going to consider the whole thing, okay? The whole structure. So what forces do we need to consider? Well, before we go on, let me change color, people. This is something which is extremely important. Usually when I write something in red, that means that it is it's something that we need to take care of, okay? So in this case, this is very important. See, right now, I'm saying that to the right is positive, upward is positive, and the rotation in this direction is positive, okay? These are very important for the external forces. Okay, what forces do we have in the X direction?
B.
Miss Acuña, what forces do we have in the X direction?
The reaction in A and reaction in B.
No. What forces do we have in the X direction? On the system, acting on the system. Yeah. Is this positive or negative?
Positive.
Yes, so that's that. What else? What else? What else? In X direction. Mr. Carranza, what else do we have in the X direction? Of course, this is this one, right? Positive or negative?
Positive.
Yes,
R,
so
K,
it's going to be
X.
plus RIX. And there's nothing else, so that has to be equal to 0. So that immediately means that the reaction in X is equal to minus P. So this is an external force. That means that we assume, okay, that's something that we have to do. You recall from solid mechanics. When you do not know something, you assume it in the positive direction, okay? So that's why I put it to the right and in the upward direction. And this relation is telling us that this is wrong. So if you make sense, right? If you pull to the right, this support has to pull to the left in order to keep this in equilibrium, okay? And then we can apply summation of forces and then summation of moments. And for this, we have to consider a certain point through which we're passing an axis. An axis has to be perpendicular to the plane. So it's always a good idea that when you do this, you specify, for example, I'm going to pass an axis, perpendicular axis to the surface through this point, okay? In this case, these two components of the force, they don't have arm. So they're not going to participate in this case. So this is very important, okay? You said summation of moment, that's incomplete. You have to say summation of moment through point A or B or whatever, okay? And this is equal to 0. And in this case here, what can you calculate using this equation? Mr. Carriel, or Mr. Chicaiza, using this equation, what can you calculate?
We need to calculate.
What can you calculate?
I don't know.
No? Oh man, you are in trouble. Come on.
Reaction in B.
Exactly. So from here, we got the reaction in B. By inspection, reaction in B is going to be positive or negative. Miss Acuña, the reaction in B is going to be positive or negative?
Positive,
Why is that?
because the system I was considered say that the reaction is to up and the force in Y is positive.
I'm sorry, I didn't understand quite well, but yeah, it is positive, definitely. Definitely is positive. I'm going to include another, because I need more space. I made a mistake when I was preparing these transparencies. Yeah, that's better. Okay, now I have more space here. See, the thing is this, okay, if I do this, okay, that's positive, that's positive. So in this case, the moment generated by R sub B is positive or negative? Let me ask, but from the, oh man, Mr. Medina, if I do this summation of moments through point A, the moment generated by the force P is positive or negative?
Negative.
Negative. You see, is this correct? Miss Puerta, do you agree with that? Do you agree with that? See, P is
Yes.
here. No, come on. You see, this is the positive moment. This is positive. And you see P here, with respect to this point, P tries to rotate like that. So P is going to be negative.
Yes, negative.
It's negative, yes. Mr. Nieto, how about R sub BY? This one here, this one here. We generate positive or negative moment. R sub BY. Mr. Nieto. No, it's not here, Mr. Nieto. Okay, please, Daniela Sayo, if somebody doesn't answer, take them out of the session. It's
Okay.
just like that. I don't want anybody who is just sitting here. Mr. Chicaiza, RB sub Y, this component here generates a positive or negative moment.
This is positive.
It's positive, yes, because you can see here,
Yes.
we are passing an axis through that point. So this is the moment that will generate R sub BY. So this is positive. And these two has to be equal 0. And from here you can get RB sub Y. So you got RA sub X, RB sub Y, and this one here will allow you to calculate RA sub Y. And that's it. So that's the way we can calculate. Okay, now, in this case, RB sub Y is going to be positive. See, I'm going to write it here. And finally, summation of forces in Y has to be equal to 0. Question, this one here, RA sub Y, is going to be positive or negative? Mr. Ramirez, Jose Ramirez, RA sub Y is going to be positive or negative?
Positive.
Why is that? Why is that? See here, what forces do we have here? The summation of forces in the y direction. No, Mr. Iturralde, what forces do we have in summation of forces in the y direction?
Just A and reaction in B.
So we have this and that, okay? And
Yes.
we know already that RB sub y is going to be pointing upward. So RA sub y has to be pointing downward. So it's going to be negative because this with that has to be equal to 0. I'm not going to do the numbers. I allow you to do the numbers, okay? Now, everybody, I'll give you a couple of seconds, okay? So let's make a cut in here. So we're going to consider the internal forces in here, okay? So let's make a cut a little bit to the right. Have here the support on the left. This is support A. Now, include the forces here and tell me the internal force in the X direction, in the Y direction, and in the Z direction. Please tell me if these are going to be positive or negative. Are they going to be in this direction or in the opposite direction for this piece of the system? Take a couple of seconds and then I'll ask somebody to participate. Mr. Medina, tell me, do you expect P to be positive or negative here? Mr. Medina, do you expect P positive or negative?
B positive.
So this one is positive. I'm just going to write, okay? I'm not saying that that's correct or not. I'm just right. Okay, and how about V? What do you say about V? Is this positive or negative? This one here, V. V is going to be positive or negative? What do you say?
Positive.
It is positive also? Okay, so this is also positive. Okay. And finally, M sub Z, you take it positive or negative? What do you say? Positive or negative? Mr. Paredes, do you agree with these two signs for P and V? Mr. Paredes, Luis Paredes, are you there?
I'm sorry, doctor.
Come on. You have to be alert here. I don't want to waste time. We cannot waste time. Mr. Tubon, do you agree that P is pointing to the right in this case? Mr. Tubon?
Yes, Mr.
You agree with this? You think?
Yes, I agree.
And what about M sub Z? Do you think it's positive or negative? Mr. Tubon?
Positive.
It is positive. Okay, let's see. Okay, now, how do we do this? Well, what we have to do is, in this piece, this segment, or this section that we're considering, what we have to do is we have to include all the forces, okay? So what forces do we need here? Well, the reactions. That's why we did this. The first step was to calculate the reactions, okay? So here on the point A, we have two reactions, R sub A X and R sub A Y. So we calculated that R sub A X is negative. So here here, this is R sub A X, because it's negative. And we said that R sub A Y is also negative there, pointing downward. So if these points in this direction, makes sense that these points in the upward direction. If R sub AX points in to the left, makes sense that this points to the right. Okay, now how about this one here? Well, we still need to calculate, because this pair, V and RA, makes us to go in this direction. The other, sub AX and P, to go in the other direction. Okay, so this one here, we will see. I am not sure about this one. We will have to do the numbers with these values in order to determine if MZ is positive or negative. Okay. Before we go on, okay, to the next example, let me try to erase here, because there. Okay, let me go on back to, let's change color. Okay, let's suppose that we want to analyze the right part of the system. Okay, so from this cut, AA to the right. So in this case, we will have something like this. We'll have downwards like this. And here I have these supports, but this support can move this direction. To the right, we have force. I don't like this P. Let's call it F. And here we have the cut. Okay. And in general, these forces will be acting on this cut, but looking at the other side in the opposite direction. So we're going to have a V force pointing downward and a force to the left, like this one. Okay, so this is the same as this one. This is the same as this one. Okay, and now the problem comes now if I ask you, is this P positive or negative? Well, the thing is this is the same as this one, but that depends on the phase. Okay, and that's what we will discuss in a minute. That's what we call the sign convention. Okay, that's something that we have to agree. So to solve this problem, because this P is the same as this one, we will have to agree. We have to agree in a sign convention. What do we mean by this? Well, we have to agree.
Excuse me, doctor.
Yeah.
I have a question. Why does the direction change in the point A? Because at the beginning we had in the other direction RAX, RAY in the point A.
No. Yeah, the problem is this. When we started the problem, okay, we didn't know these values. And when you do not know something, it's a good practice to assume them as positive. Okay, so what we're saying here is that when you calculate and you say that this is negative, that means that this is the real value of RAX is the opposite to the value that we assume. This is an assumption. We assume that it's pointing to the right. And when we calculate it, we notice that this is negative. That means that in the real situation, this is opposite, because this is negative, to the value that we assume. This is assumptions. These are the values after we have applied all these relationships for equilibrium.
All right.
Okay.
Okay, thank you again.
So that's why I wrote this in red. So we assume if you do not know something, you assume in the positive direction. And the equilibrium will tell you if this assumption is correct or not. Okay? Good question. Good question. Okay, so we have to agree in a sign convention. Okay, and in this case, we will see that we will talk about phases, positive or negative. Okay, and you see that, for example, this card will define and what we call a positive phase, and this is a negative phase. So we're going to say that if the force in the positive phase points in this or that direction, we're going to call it positive. And immediately you can go in the other direction. If you consider that the phase is negative, those forces to be called positive, they have to point in the opposite direction. Okay, so in this case, even if you consider a positive or negative phase, if you say this is positive, you know exactly what we mean. Okay, let's go to the next example. Let me erase. Okay, so we're going to do this. So we're going to do this. Let me move upward. Okay. Okay, now let's see. Up in the list. Here we have Mr. Fuertes. How many reactions do we need to calculate in this case? How many reactions? How many reactions in this case we have to calculate? Mr. Fuertes.
4 reactions.
4. Okay, so those are, of course, the reaction here. Okay, let's go to start
Reaction
by what we have to
AX, reaction A wake.
Exactly. So let me put here.
Reaction
here.
and
This is the reference system. Okay. This is the reference system that we're going to use. It usually is the same, but from time to time we can change. So it's a good idea to have it. So if we do not know the reactions, we assume positive, positive. So this is going to be RAY. This is RAX. Here, R sub C Y, to the right, R sub C X. So we have 4 reactions. So right now, this is an statically determinate or indeterminate system. Mr. Chin Chin. Mr. Chin Chin. Right now. Indeterminate. Indeterminate, because we have only three equations. Those are summation of forces in X and Y and summation of moments. Now, but the problem is that this problem is taken from this chapter in Popov's book. That means that we can calculate them. Okay, now this has a special characteristic. This is a hinge. So in a hinge, we do not transmit moment. Okay, this is something that probably you remember from your solid mechanics class. Hinge transmits force, okay, does not moment. Okay, so usually when you see a hinge, that means that it is very interesting, this thing, because it doesn't transmit. Okay, everybody, let's do a free body diagram of the element BC. So let's do a free body diagram of element BC. Okay, so here, that's a really terrible element. Oh man, somebody keeps bugging me, please. Damn it. You don't want to be here, get out of here. So this point here is point B. See? So we are like considering just the part of the system. And through this pin or hinge, we transmit only forces. So this is point C, and here we have two forces. These are reaction Y and reaction X. Now, here, how many forces do we have? How many forces and moments do we have here? Well, since this is a hinge, okay, we do not transmit through this pin, we do not transmit moment. We only transmit force. Okay, so we are going to have, let's call it a force B in X and also a force B in Y. Now, let's suppose that there's something, it doesn't say the problem, but let's suppose that we neglect the weight of this element. Okay? Now let's suppose that the weight of this element is very small compared to the forces that we're applying. In this case, 15 kilonewtons and 20 kilonewtons. Let's suppose that it's very small. A question for you. Can you draw me the direction of the forces in B and C so that the system is in equilibrium? Can you write me? Can you think, okay, how the forces in B and C? See, I know that there are two components, but you can combine them, okay? You can combine them and produce a single vector in B and also in C. Can you visualize how this vector should be in order to have B, C in equilibrium? Sequenza, can you say something about it? Can you visualize the force in B and C so that this element BC is in equilibrium, sequenza?
They are opposed to each other and is equal to 0.
Exactly. Now, just a second, please. Just a second. So they have to oppose each other, definitely. Okay, let's go Amarillo, Barcelona. Okay, so that means that the combination of these two has to be pointing in that direction, and they have to pass through this point. So as you're saying, they have to cancel each other. So what we can assume is that these two components, they have to produce a vector like this, and here we're going to have a vector like that. That's the only way, okay, you can draw the line of action of these two vectors. This is the only way, in this case, with only two forces in B and C, this element could be in equilibrium. Okay? If they have a different direction, okay, so then we're going to have a net, at least a net moment that is going to make it rotate. So if we want this to be in equilibrium, they have to be aligned. Okay? So forces at B and C must be aligned if the system is to be in equilibrium. So that means that if this is the direction, okay, we can calculate the angle that is formed here. Let's call it theta. Okay. So theta can be calculated. Can you calculate theta angle, Mr. Jarry Cedeño? Can you calculate theta?
Yes, if I know the X value and Y value of the.
No, no. Look at the geometry. Mr. Aizaga, Gianni Aizaga, can you calculate theta?
Yes.
Yeah. Aizaga, can you hear me, Aizaga?
I can hear you. Yes,
Okay,
I think.
Can you calculate theta? Can you calculate theta?
I think yes.
How can you do it?
I have the reaction in.
No. You don't know the reaction.
The geometry of the triangle.
The reactions.
The geometry of triangle.
Mr. Kimi, can you calculate theta?
Yes.
No, don't write, Romero, don't write here. Don't write here. I don't like it. Okay, I'm the one who's going to write. Okay, go on. Whoever was talking. Mr. Kimi, can you calculate theta?
Yes.
Tell me how.
With the.
Come on, you have a triangle here.
Yeah, the triangle.
The tangent.
It's a tangent, inverse tangent, or whatever.
Yes.
So theta is calculated. And then
X.
And the theta is the same angle as this one here. So that's the same angle as this one here. So how would you relate, Mr. Fuertes? How would you relate RCX and RCY? RCX and RCY. How would you calculate them?
Sorry, Mr. Can you repeat?
No, I cannot repeat. I cannot repeat. I don't have the time to repeat anything. Mr. Chikaisa, can you relate? How do you relate RCX and RCY?
3,000 divided by 4,000.
No. See, the thing is, remember, in yellow, we're saying that this is the vector, okay? This is the direction of the vector. And this has to be aligned with this force. So this vector has this angle, is forming this angle with the horizontal. So RCX and RCY, they have to have the tangent between these has to be the negative of this angle. Okay, because here you have to the right and here you have upward. So you're saying is that RCY has to be negative RCX tangent of theta. Are we clear, people? Let me see. It's not clear. This I'm going to write it again. So this is RCX. Why? Because the triangle here defines the direction of this vector. And this vector is composed of this and that. Align it. Okay? In this case, we have an extra equation combined with the 3 from the equilibrium equation. We have 4, and that's equal to the number of unknowns that we have. So originally, we thought it was statically indeterminate. But considering this relationship between the components, yes, we can include another relation, and from that we can calculate all the 4 reactions or the 4 components of the reactions. Okay, is there any questions about this? Otherwise, we're going to have a break, a 5-minute break. It's 8:05. We're going to start at 8:10. Okay. If you have any questions, please ask them when we return. Daniela Sayo, please stop the recording, and when we return, you can start recording again. Okay. So 5-minute break, people, because I need a break for my throat.